My name is Arunachalam Ganapati. I work for ARM, and today I'm here to discuss about the new feature, device assignment in ARM CCA. So here is the agenda. I'll briefly cover the introduction of what ARM CCA DA brings in to the ARM CCA, and also we'll talk about the brief on the industry standards and the specifications. And then we'll spend the major time on how this feature is implemented in TF-RMM, mainly discussing the role of TF-RMM and how the implementation has gone through. And we'll cover some of the ABIs that RMM specification has come up for this particular feature. And we'll finally cover a little bit about the TDISP state, how RMM maintains the TDISP state for the devices that are assigned to the realm. And then we'll cover a little bit about the device attestation evidence, what it has, and how it is used by the realm later on. And finally, we'll wrap it up with the status and how we can replicate the latest CCA stack on an FEP. We have some shrink wrap-based utility to replicate it. So let's get started. On the brief of the introduction to CCA DA, so you can see in the right-hand side, which is the current state of ARM CCA 1.0, where RMM is in REL2, and hypervisor can use some RMI commands to launch a VM in the realm pass. So this provides confidentiality on CPU registers and as well as the memory. But what is not included in this is the device itself. This picture is drawn keeping device in mind. So the device is completely out of realm's TCB. One way to support such devices across different CPU architecture, what they adopt is to use bounce buffer mechanism. And what here means is, in the realm, part of the high VA is being shared with the hypervisor. So that way, the device can talk to the driver in the realm. So what this brings in is, this automatically puts the hypervisor inside the TCB of the realm, because the moment the content is DMA'd to the high VA, that is visible to the hypervisor. So in a degree, we need to trust the hypervisor, and when we say we need to trust the hypervisor, we end up trusting the cloud service providers as well. The same thing happens for MMIO as well. Whenever the realm wants to talk to a device through MMIO or DMA, it has to use the same bounce buffer mechanism to communicate with the device. So what ARM CCA DA brings in is to remove this bounce buffer mechanism and also to get hypervisor out of the TCB and puts the device into the TCB of the realm. And this is done with based on variety of industry standards and as well as based on ARM standards defined by the RMM specifications. So as I mentioned, it is going to extend the TCB of realm by bringing in the device into the TCB. The first and foremost step is to authenticate the device. So that we'll cover later on how that device attestation evidence is collected and how it is verified. This brings changes across the software components. Pretty much everything in the stack needs a change. The RMM mainly, it implements all of the RMI commands and the RSI commands as mentioned by the RMM specifications. And also the hypervisor needs to be changed because it needs to initiate all these management commands to assign a device to a realm. Same thing happens with the realm as well. The realm has to implement the RSI commands to retrieve the measurements of the device and move the device into a particular log state or a run state, and finally accept the device into the realm TCB. This also brings in some changes to the system components as well, mainly the SMU and the root port. The root port has to be compliant to ARM RME system specifications. So a whole lot of changes has been done to enable ARM CCA DA. So that brings me to the next slide. We'll cover the brief about the industry standard and specification. I won't go much details into each of it. In the left-hand side, we can see a number of specifications from PCI SIG. Those has been engineering change request in the specification, and later on it has been merged to the PCI specification. And in the left-hand side is the ARM specification based on the industry standards. What are the changes that's done in the RMM specification and as well as the RME system architecture? To begin with, I would like to classify all the specification into two parts. One is the one that provides confidentiality to the data plane, the other one which provides confidentiality to the control plane. So when we talk about the data plane, I would like to talk about the IDE, which is the separate hardware, which is both present at the root port as well as at the device. So what this brings in is it protects the link, basically, by encrypting the data that moves on the link, and as well as it provides the integrity, so that it prevents the data being protected from the replay attacks. So mainly the TLBs or the transaction layer packets, which are the first layer in the PCIe stack, gets encrypted when it passes down the link. And there are various other specifications as well, the CMA, the DOE, SPDM, and TDISP. I would like to talk about the TDISP, which is like an umbrella of specification. It refers different specification, how the entire stack needs to be built. It sets up the rules for the TSM, which is the TE Security Manager, and it tells the rules for DSM, which is the Device Security Manager, which is mostly used in the device manufacturing stage. It provides the rules and regulation on how, when a device, when it needs to be accepted into the realm TCP, what are the criteria it needs to meet, right? And the CMA, DOE, and SPDM, they all provide the confidentiality together. They all provide the confidentiality on the control plane. Mainly, we need to access the device much before the device is being accepted into the realm TCP. So the DOE provides the mechanism to reach the device through the config space of using the config PCIe config read and write. And SPDM is a protocol which is widely used when it comes to device. It is completely a device agnostic protocol, but it is meant for a device. It uses the requester and the responder based communication. Here the requester is the software, meaning the host, and the responder is the device, which is at the endpoint. That's the brief on the standards, and based on all these standards, RMM specification V1.1 defines a new chapter called Device Assignment. It introduces various set of commands that a hypervisor can use to launch a to attach a device, to assign a device to a realm, and manage the communication state with the device. And the specification supports variety of devices, both off-chip device and an on-chip device. As I mentioned, it provides the commands for the PDEV and the VDEV management. The main thing here is it abstracts the TDI, which is the individual assignable unit of a device, into a PDEV and a VDEV. There is a comparison between the PCI SIG terminology and what it means in ARM CCA. So this PDEV and VDEV abstraction helps us to attach any kind of devices to a realm, as long as it meets the guidelines as mentioned by the standards. So just quickly run through the terminology comparison. The TE, which is the Trusted Execution Environment, refers to the realm pass in ARM CCA. Similarly, the Trusted TE Security Manager refers to the RMM, which is running at REL2. And the TVM, which is the TE virtual machine, is equivalent to the realm. And when it comes to TDI, the physical function could refers to the PDO, which is the host interface, which is mainly used by the RMI commands. And there is a TDI, which when it refers to the virtual function, it refers to the VDO in Arm CCA terminology, which is mainly used by the realm interface. So we'll move on how the implementation is being done on TF RMM. So there are many ways in which to take it forward. The one that I chose is like, how did we start with the implementation, and what are the steps, the first steps we did based on that. So whenever a device is assigned to a realm, what the host hypervisor has to do is, first it needs to do a PDO create with the RMM. What it does is, it does quite a series of steps. The first thing is to attest and verify the device so that the control plane gets encrypted, so which will be later on used to release the keys for IDE key programming or establishing a secure session. So in the left-hand side, the PDO, the moment the PDO create is being done, the PDO will be in the PDO new state, and there is a sequence of PDO communicate happens. Whenever I refer to PDO communicate, it's a communication from the RMM to the device, which goes through the non-secure hypervisor, as mentioned in this diagram. So as the very first step, the connection init happens. This happens based on whatever the CMA, the component measurement and authentication mentioned in the PCI SIG. There are a set of algorithms, and what is the minimum version of the SPDM, and similarly the version of the TDISP, and everything gets negotiated with the responder. And the next step is to retrieve the certificate. To do so, the RMM initiates the SPDM requester commands, mainly the get certificate. And the get certificate command gets passed across the PDO ABIs back to the non-secure hypervisor. Then now the hypervisor is responsible to pass it down to the DOE, the PCI DOE driver in the non-secure in the non-secure side, and that will interact with the device and fetch the certificate from the DSM. As part of this activity, the hypervisor holds the entire copy of the certificate, and RMM during the PDO communicate call, it computes the hash of this certificate, which will be later on used for device attestation purpose. And once the successful retrieval of the certificate, the PDO state, which is internally maintained by RMM, moves to the needs key phase. From there, there is a separate ABI which is invoked. The host extracts the certificate, parses the certificate and extracts the public key, and issues the new the RMI command to set the public key with the SPDM connection. Once the public key is being initialized with the SPDM connection, there are two main things happens here. One is the establishing a secure SPDM session with the device, and next is securing the IDE link. So RMM does a SPDM command called key exchange. Here the RMM generates a key and passes down the key to the DSM layer to establish a secure session. The moment the key exchange call is complete, a secure session gets established with the device. And that way, the link between the RMM and the non-secure hypervisor is encrypted, as shown in this figure. The next step is, as part of this, is to generate, the RMM generates the IDE keys, which will be used by the EL3 IDE commands through the EL3 interface and down to the PCI root port. The keys are distributed in in both at the root port side and as well as at the endpoint side, which the way in which the keys are distributed is, for the root port side, we use EL3 interface, and for the device side, we use the SPDM interspecific command called IDE key management. Using that, the keys are distributed to the device. Once this phase is complete, the entire link is encrypted between one end to the other end. And this link encryption can happen over the switch, whereas the switch could be in an it is not part of the TCP. We don't have to trust the switch itself. That way, the point-to-point communication can happen in an encrypted way. Moving on, this is just to put everything together. So the RMM supports both off-chip and an on-chip device. This summarizes what are the design, how it has gone through in the TF-RMM. There is a RSI VDAV ABIs and RMI VDAV ABIs. These are all the runtime component of the RMM. And you can see there is a libDSM, which is the interface to the device. And there are IDE commands, TDISP commands, and which are channeled through the SPDM commands. And RMM uses libSPDM to communicate, to send the messages to the device. And that's being exported as a submodule inside RMM. Similarly, the IDE and TDISP libraries are also taken from DMTF. As I mentioned here, so the transport for RMM from the REL2 to the hypervisor is the non-secure buffer. So for any command that needs to be sent to the device, RMM, what it does is it retrieves the non-secure buffer as part of the PDAV communicate call, writes the command over there, and passes the control to the hypervisor. The hypervisor then further takes the command down and pass it down to the DOE driver. From there, it gets converted into the PCI config read and write to the DOE mailbox. So there are three types of communication that RMM mainly does. One, as mentioned in the different colors, the SPDM itself goes over the DOE through non-secure hypervisor doing the proxying for the commands. And for programming the root port stream needs to be locked. There is a special ARM DVSec, which is a special extension, the PCI extended capability in the ARM root port. So that controls the bits to lock the stream. So those kind of commands are done by RMM directly by accessing the PCI config space. Similarly, the IDE commands to the root port are done through the EL3 interface. So this summarizes the device communication state inside RMM. This is a common communication infrastructure which is used for both the PDAV communicate call and as well as the VDAV communicate call. The pending state is the initial state, and it refers the RMM has some data to be communicated with the device. So this tells the host so that the host will do the first VDAV communicate call, the dev communicate call. Upon doing the first dev communicate call, the device itself, the device state moves from the pending state to active state, which sends the command to the device through the non-secure host. And the consecutive PDAV communicate call will get the response from the device, and the RMM will process the response. Upon reaching a final state, the device will again move the state from the active to ideal. This transition will complete one state transition in the PDAV or in the device. For example, from hash key to PDAV ready, there are multiple communication happens. One, it establishes a secure session, then it distributes the ID key to the root port and to the endpoint. So there are multiple exit that happens to the host, but from RMM side, there is actually only one transition that happens. And coming to the RMM role in realm device TDISP state, once the realm discovers the device, which happens by when the realm boots, as part of the device enumeration process, it will find a device, and at that point, the device will be in a config unlocked state. That is the first state where the realm will see the device, and during that state, the secure session is done. The IDE is streamed, the IDE is logged, and the IDE keys are released, which can now the realm can do a RDEV, the RSA RDEV lock, which takes the device state to a config locked state. Upon moving to config locked state, the realm can do a series of commands to retrieve the device attestation. It does so by initiating the get interface report and as well as the get measurements call. This initiates the same dev communication flow and retrieves the relevant objects from the device. The non-secure host has the copy of all the device objects, and RMM has the digest of those device objects. Once the relevant device objects are retrieved, RMM, the realm does a call called RDEV get info. This retrieves the digest of all the device attestation blob, and later on it verifies with the copy that it has got by using the RHI calls. The RHI calls are used to retrieve the objects which are in the cache state by the host. Upon receiving these commands, the realm gets the complete device attestation blob. The reason why it is kept in the non-secure host is the attestation blob can be huge in size. The certificate can be 64K, the measurements can be in 64K to few megabytes, and same thing goes with the interface report. Once the realm retrieves verifies the digest, it can go for a remote or a local attestation that is up to the realm and the realm owner. Once the attestation is done, that is the key point over here. It says whether it's a yes or no. Once the attestation goes through, the realm accepts the device into its TCP by issuing a RDEV start command, which moves the realm to a run state. And this is about the device attestation evidence that I talked about. Mainly it has the device certificate. It's a device certificate chain, which is the format is X509, and also the device measurements, the TDISP interface report, and what its format is. As I mentioned, the objects are cached by the non-secure host as the RMM communicates with the device, and RMM has the digest of all these device objects. And so here I would like to quickly cover the current status. So although the spec supports different type of devices, the PCI off-chip device and on-chip device, and there are also support for CXL in the spec, but the implementation here we have enabled the ABIs only for PCI off-chip device. And what has been done so far is we have enabled a secure SPDM session, IDE key management, TDISP, and also root port IDE key programming. Some initial support for DVSec is also there in the current branch, which is in upstream. And here is the public development branch, and there is a shrink wrap instruction on how to build this report together to demonstrate the entire flow, and the right side of it has some of the logs, which says the first is about the libspdm start session, which says the secure session is established, and the second part of the log corresponds the IDE keys are distributed to both at the endpoint and at the root port. And the third log says the realm discovers the device as part of the PCI enumeration process. And the fourth, the realm issues, verifies the digest and issues a start command which accepts the realm, which accepts the device into the realm TCB. And here is what next in case of when it comes to the features. The immediate thing that is planned is to harden the existing stack which is there, and also to align with RMM specification alpha 13, which has the host initiated VDOV flow. This aligns with the latest and what the other CPU architecture has, and how the flow happens when the realm has to accept the device. And also there is realm DMA support that is being planned, and the SMU driver support which is also planned immediately. And there is also a plan for to move the device device assignment libraries which are in RMM to deprivilege to an lower EL, mainly at EL0, using the app framework. There is a talk tomorrow on this by Sobi Matthew. And on the testing front also, there is existing TFTF, which is the bare metal test cases, which exercise most of the host side and the realm side ABIs. That will be soon published, and there will be a shrink wrap overlay for it as well to test all the changes. So that brings me to the end of this talk. Please let me know if you have any questions.
Anyway, I will shout out. In line 13, you have the Linux prototype mentioned there.
Yes.
How do you expose the evidence to the user land?
You mean the device attestation evidence?
Yes.
The realm issues a series of RHI commands, the host interface command. So the realm directly talks to the host. There is a separate specification for it, which is the RHI specification. And there are different device objects which are mentioned in the specification. So the realm makes a call, RHI call, issuing a particular device object ID, for example, certificate. Upon issuing that command, the host retrieves the certificate and passes it down to the realm. The same thing for the measurements and as well as the interface report.
But how is that abstracted to the user land? So is there
You mean to say a sysfs kind of interface?
yeah.
Yeah, okay.
Yeah, maybe it's quick if I just answer this one. There's some general work going on from Dan Williams at Intel with some of the AMD folk and ARM folk on standardizing that. So it is, as you said, it's a sysfs interface. But there's probably going to be some stuff built on top of that because it's getting too complicated. So it may end up as netlink. Anyway, sorry.
Okay.
So at the beginning you were mentioning about RMM and
Yes.
Also the REN. I believe that REN is also EL0 and EL1. You were specifically mentioning EL1. Was there a specific reason for that?
No specific reason. Just to show that there is only the EL0 is one that is doing all these calls. Just for that purpose, I included only the EL0. Sorry, the EL1 part of the realm.
Okay, that's
So
fine.
that's the code that issues most of the commands to the RMM. Right.
Okay, And is there any possible security attack if I do not have runtime measurements accounted from device perspective? Like I'm thinking about the presentation that I gave, like if the connection with the, so SPDM is within the tester, that you have the device, you have the REN, but talking about the user perspective, which is the relying party, is there any attack possible if I use a protocol which does not take care of the runtime measurements and the device attack, the device that is attached? Someone could attach a malicious device that a user is not aware of. So is there something that you have done? Have you done some security analysis of these kind of cases?
No, what happens is, even when there, let's say if there is a malicious device which is being attached, and as part of this entire flow, the realm will get all the measurements from the device, right? And later on, it has to present all the measurement blob with the verifier. And
that happened before already, like in the
before,
for example, for the pre-handshake attestation, it never knows what is going to be connected at the runtime, and even in intra.
IDE collapses, you lose all connection.
Sorry.
The moment you switch the device, IDE collapses, you lose the encryption because it doesn't know the key.
Oh, you need to establish a new connection after every.
You have to
Okay.
do the whole thing again.
Okay. Thank you.
okay.
Cheers. A couple of things. One, I'd be wary on statements on CXL TSP, because the model for that is quite different to TDISP. It's intended very much for a firmware mode, because the idea is it's just memory.
Okay.
So, yeah, a little bit more on that. The other one is LIS25 as an implementation is a great reference library. I've used it myself, but massively over the top for the RMM, because most of the complexity in SPDM particularly comes at the device end, because you have to support everything a host might do to you.
Yes.
A host only has to do one thing.
Yes. That's
So definitely worth exploring simplified solutions to that.
Agree. Yeah. The SPDM, lib-SPDM itself is a reference software, and the context is quite huge. I mean, there are a lot of ways to optimize it.
Yeah, you don't want that.
When we implement our own SPDM.
Yeah, so maybe two technical details. First, just for my curiosity, how are interrupts handled in all this setup? So what makes the LPI go to Realm rather than anywhere else?
What makes the?
LPI go to Realm rather than anywhere else. So how do you secure the interrupts?
Oh, the interrupts part and the DMA, those are not at there. Yeah, we are currently working on it. You mean to say the MSI interrupt, which okay.
Okay, and then maybe the other thing is, can all this song and dance work without all the SPDM and TDISP nonsense?
Without? Depends on which kind of device that you're.
So basically, I have a normal device, let's say a network adapter, who I don't really care if anybody's spying on me. So can I just put it in there, do the whole?
It won't work.
If it's a normal device and you don't care if anyone's spying on you, you just don't make it a trusted device. You keep it in the thing with the bounce buffers and run it. Then you need to trust it, because it's accessing any of your memory potentially. So you've got to do something. It doesn't have to be this stack. But this is there.
Even the attestation is fine, but encryption seems over top for.
Look at a whiteboard. There's no way around it.
We're running over into the next session, so we need to wrap up. The next speaker's time.
We can follow up later. I wanted just to know if you've got any consideration for key rotation for IDE in this, because IDE lets you have 2 key slots, right?
Yes.
And does the current design support key rotation?
Yes, it supports.
Okay.
It supports key refresh, but it has to be initiated by the host. The current implementation, we are working on how a more trusted component can initiate this key refresh whenever the IV vector runs out.
Including a realm. A
Yeah.
realm could initiate as well.
Okay, yeah, that's something new.
I think you want to think about that, though.
Okay,
All right, cool.
cool. Thank you. Okay, thank you so much. Thanks for your attention.